Hello everyone, and it's been a while since I talked about Houdini. So today I want to start fresh. I want to start with rigid bodies today. So first I will talk about what are rigid bodies, then we will expose ourselves to the very fundamentals of rigid body and we will create something. And I will explain what we are doing, why we are doing, and why do we need it. So let's start with what are rigid bodies. So, rigid body is basically any object that stays solid and keeps its shape during a simulation. Like, imagine a stone hitting a wall. The stone doesn't bend, right? It either bounces or it breaks. In Houdini, we use RBD to create massive destructions or simple physics. So, let's just look how we can set that up, right? And okay, so let's start fresh, right? Let's start with a sphere. I have the sphere, and what we can do first, we need to break this sphere into pieces. So the very fundamental says that if we want to break something and we want to like break something into pieces, then we have to have the pieces already set up for us. So when we simulate, when the gravity or forces work on that object, so those pieces can like break and we can like have the freedom and to direct how our pieces will look. For example, if I want to like break this sphere into two pieces, then we need like those two pieces. So after when the sphere hit the ground, it breaks into two pieces, right? So we have to have those pieces already like separated, right? So first, what we need, we have the sphere, and to like break the geometry, we have different methods. And first we will start with the very basic method we can like understand, you can understand, and later in this like series I will create more videos covering different fracture methods. So I have the sphere, and what I can do right now, I just want to like transform this ear, actually translate this ear through transform SOP node, and I want to put it right there. So let's just create a transform node and translate this into the positive y axis, something like here, right? What is this? Why do I have this point? What is this point? Yeah, I don't know. Okay, so we have our sphere right there. What I can do, I can just create a null, so we can have like we can have the reference where our sphere was. And after the transformation, I want to talk about the Voronoi fracture. For the Voronoi fracture, it is the like a method to create those pieces. First I will do it, then I will talk about how I did it. Forget, just don't focus on this. This is just I was working on something. Okay, so let's create some points, and we need two things. We need points, and that will be our seed points for the Voronoi fracture. And what are seed points, I will explain, so no need to worry about it. Just let's create some points. Scatter. Now we have points onto the surface of the sphere, and you will see the total force count is 1000. Let's say 10 for now. So I have 10 points on the surface of the sphere, and right now we are generating these points by density. And just turn this relax iteration off, because we need to have these points randomly placed on the surface of the sphere. And here the really important thing comes. We have two ways to distribute the points. We can distribute it on the surface of the sphere, and we can distribute it inside also by creating a volume first. So I want to talk about this surface method first. I have the sphere, I have the geometry, and now a new node, Voronoi Fracture node. This Voronoi Fracture node need two things: seed points and our geometry. This first needs geometry to fracture. We have this geometry to fracture because you see, this geometry is already placed in the y-axis, in the positive y-axis, but this is just this geometry. This is for the later. We don't need to have it right now, so just forget about this. And we have two things. We need two things: our points. These are our points and our geometry, right? Okay. So you see here, Voronoi fracture, we have some pieces together, right? And these pieces are created by the sphere. When I say exploded view, so we can see these pieces like separately. When I say the exploded view, the uniform scale is set to 1 right now, sorry. You see we have different pieces. And when I turn this visualization off, you will see we have these pieces. So this visualization is currently set on this attribute piece, and it is giving it a random color, and how and where, from where this piece attribute came from. You see, when I open a geometry spreadsheet, we have these, these pieces attribute, and these piece attributes are on the primitive level. So when we create the Voronoi fracture, this Voronoi fracture also creates an attribute by name on each piece of the geometry. And here I now want to talk about how this Voronoi fracture works. So we have our geometry and we have our pieces, we have our points, and these points will act as seed points. So these seed points will be on this sphere, and these seed points will create a piece, and this each piece is called, we call each piece like a Voronoi cell, and how it actually works. So let's say you have a sphere, right? You have the sphere, and we have a single point inside the sphere, right? Or let's say 2 points on the sphere. So what will happen here? This 3D space is filled with like invisible points, right? So each point will calculate the distance of this 3D space, right? So if a point is inside the geometry or on the geometry, and it will look like which point is closer to the seed point. So if I'm checking this point right here, and we have two seed points, 1 and 1. So these seed points will look for points in this 3D space, and whichever seed point has the closest distance to this point, it will be in that point cell. So each point represent a cell, and each point look for the values inside this 3D space, and like the closest point, these 2 points will search for points in this 3D space, and whichever the point is closest to it, it will already be assigned in that cell. So if I'm saying that I have two like points, and when I explode this view, you will see now we have 2. So these I can say something like I want to have a wireframe. So you will see wait a second, I can just see. So these 2 points, you see, these 2 points are right here, right? And when I'm saying something like this, so these points are calculating these point distances. So they are looking for points in this 3D space, and whichever point is closest to them, like they are assigning those points into their cell. So if this point is closest to this point, the seed point, this point belong to this seed cell. This is how like the Voronoi fracture works. And just toggle this on, and I want to say smooth wire shaded, and now we have 2 points. In the next part, first I want to talk about the packed geometry and this unpacked geometry, and then I will cover the other fracturing methods. And here uh, a really important thing here also, just remember this Voronoi fracture, this Voronoi fracture is creating two pieces, right? And each point, each seed point will create a piece. Each seed point will create a piece. If I'm saying 10 seed points, then we will have 10 pieces of this geometry. And you remember I scattered these points onto the surface of the sphere, and we have two things. We can spread the seed points onto the surface of the object, or we can have these seed points inside also, like inside of the sphere also, inside of the object also. And what do I mean by that? Let's say we have these points, we have these points, and these points are like outside the sphere, right? So when I increase the the total force count, you will see we will have really sharp pieces, and they will be joined at the center. And what do I mean by that? Just increase those pieces and you will see these pieces, these are like long shards, and they are facing like the pointy point, like the pointy structure is facing at the center of the sphere. And why this is happening? Because these points are at the surface, and when you like visualize this, how these seed points are working, you will see when each point calculates like which point is closer, they will create this pointy structure. When you like increase the seed points, just imagine this, just I will say take a paper and a pen and just visualize this, just create a geometry and a seed point, and just draw some lines and see which point is closer to which point, and you will have the exact idea why we are creating these shards type of pieces. But we don't want that. What we need chunky, boxy, random pieces. So to do that, we need to scatter these points not only on the surface but inside of the geometry. And how we can do that? This scatter node works. How this scatter node works? First, we need to understand this, how this scatter node works. This is the SOP node. So this is modifying or like creating a geometry, and this is modifying this geometry by creating points onto the geometry, right? So the scatter node here is creating some points on this surface of the sphere. So right now it is calculating the surface area and it is placing seeds according to the surface area. But when I create a volume, and we have two methods to create volume, we can create an ISO offset, and this will be the what's the word, the non-efficient method, and the efficient method is volume, what's the VDB from Polygons. Okay, so we have two methods. The efficient one, VDBs, it like requires less space and more efficient way. I have talked about this in the volumes in like detail. And we have the ISO offset. So this ISO offset is creating the fog volume. This is also creating a fog volume, right? Right now we have the distance VDB, and now I want to talk about how this scatter will work when I connect this into the surface SDF field value. So basically, precisely this scatter SOP node now looking for the values inside these voxels. What it is looking for, it is just looking for a value that is inside the voxel. Right now we only have the density value, and this density value is coming from the SDF surface density field, or we can create a fog VDB density, but here the SDF values are in positive, negative, and neutral, which is 0. So when I talked about the VDBs from Polygon, and when I talked about the SDF values, surface distance field values, you will see these voxels have value. All the negative values we will see, and all the positive values we will not see, and all the values which are 0, the voxels onto the surface I talked about in the volume video. These voxels which have 0 values, 0 SDF values, will be visualized here. So you are seeing this, the surface of this sphere have the SDF value 0, that's why we are seeing this, and inside this sphere we have negative values. And scatter is just a probability. Scatter is looking for just a probability. So what makes it more probable that the points will be scattered in these voxels? Like if I'm saying what is the probability this voxel will get a point, and this probability depends on the value of the voxel, the density value those voxels contain. So this VDBs have negative values inside, so it will not consider the negative values. This needs positive values. It doesn't matter, it just need positive values. It doesn't like what's the word, it doesn't think about, it doesn't care about just negative values. It sees negative as 0. So scatter here, when I turn this off, you see we have these points. These points are like on nearly at the surface, they are not deep inside. And when I create the fog, and you see now we have points inside the sphere. And why? Because fog value inside these voxels, the voxels that are inside the surface have the density value which are in positive. That's why we are seeing the fog, right? You see this fog value, these values have density, these voxels have density in positive. That's why we are now scattering point inside also. That's is what I wanted to explain here. Whew. Okay, now we have this ice offset. You can create the SDF and fog volume is just the same, but to be more efficient, just use the VDBs. And we have now scattered some points, and I will say I want 10 points, so we will have points inside of this sphere also, and we will see something like this. So if you increase the point number, you will see something like this, not those shards type pieces. So I think I have covered the very fundamentals of this. And if you want to see this in simulation, what you can do RBD Bullet Solver. This is a DOP node. Just see this. This is just for the example, and ground type, ground plane. So we will have this ground plane, and toggle, just bypass this. So you can have your sphere intact, and when you play this, you will see it will break down. So now the gravity is working onto this, and these are rigid bodies, so they won't like bend or something, they will break or they will bounce like this. They're bouncing, but they are not bending. So I think I have covered the very basics of the rigid bodies. Just understand this. We create points inside also if you want to create some natural pieces from the geometry, and we will use the VDBs, which are more efficient, and we will use the fog volume, not the SDF volume. Okay, so in the next part, I will cover Voronoi fracture in depth, and into the upcoming videos, I will also cover the different fracture methods, which is really important. So just understand these, right? Understand these, that this Voronoi fracture also create the name attribute on the primitive level, and each piece has this name. You see this piece 0 has this piece, and piece 1. How, if you create more pieces, then you will have more these attribute. So yeah, and in the last, I want to say that each piece you can say it is a Voronoi cell, right? Because one seed, one Voronoi cell. So I guess this is it for the video, and I will see you in the next one. I hope you learned something. Just keep learning and just expose yourself with this software, because it can be difficult. But if you want to like go into the deep, then you have to push yourself and expose yourself with all these concepts. I do the same. I'm trying to do the same. And I guess I will see you in the next one. Until then, take care and just keep creating and learning.